I'd like now to talk about some coordination chemistry. Now, coordination compounds are compounds that have metals and then things attached to those metals. Now, when we're drawing out the formula for a coordination compound, everything that's attached to the metal is in the square brackets, and then everything on the outside is going to be outside those square brackets. And I'll talk about what's on the outside here, but we usually consider them to be counterions, and I'll explain what that means in a second. So if you look at the kinds of ligands, ligands are things that are going to attach to the CO, or the central metal atom. You'll see that they're by and large negative or negatively charged. And if they're not negatively charged, then they have a lone pair of electrons, like ammonia and water do, that can add on to the central atom. Now you've got to remember that these are metals, so metals are positively charged, generally speaking, which means that anything attached to them will be negatively charged or partially negatively charged. So here is an example of the structure. So I will just go ahead and show you that, and then I'll show you also how to figure out what the charge on the central metal atom is. Alright, so here's our compound. Let me show you first of all how to figure out what the structure is. So we've got a cobalt. As I said, everything in here is what's attached to the cobalt. And what we've got is a total of 5 ammonias and 1 cyanide. That's a total of 6 atoms attached to the cobalt. So we draw the cobalt, and now my next thing is to say, well, if we've got 6 things, how can I put those 6 things around the cobalt so that they're as far apart from each other as they possibly can be? And the answer to that is to use what's called an octahedral arrangement. Now the order of these doesn't really matter so much. It will in other compounds, but not this one. So there's my 5 NH3s, and I'll have the CN sticking down here like this. Now what I've tried to do here is show the 3 NH3s and the CN. These are all in the plane of the screen. This NH3 is sticking back and this NH3 is sticking forward. Now we can figure out what else we've got. We've got 2 BRs, and from the table that we were just looking at, we can see that BR will have a negative charge. So we've got 2 of those. That's 2 negatives, which means whatever else is in here must be 2 positive. That's because all of these charges have to even out. So that's 2 positive there. Now I can figure out what the charge on the cobalt is, and I can just do a little math here. I know that ammonia has a 0 charge, so I'll know there's 5 of those, but that's 5 times 0. We have 1 CN, which has a negative 1 charge, and all of that adds up to positive 2, because that's the charge on everything that's in here. So cobalt is now going to come out to a 3+ charge. Alright, so that gives you an insight into structure. Now that's not all we're going to say about it. Let's take a look at some of the other things that we need to consider. Also, I mean, when you've got a molecular formula, there's no real reason, sometimes you really can't tell what the structure of that molecular formula is, and sometimes we can be subject to what's called isomerism. Now isomers have the same formula but different structures, and in a couple of examples of isomers. First one here, this is called anion exchange, or getting an isomer by anion exchange. And what we're doing is we're taking something negative that's attached to the metal, but it has to have a negative 1 charge, and replacing it with something on the outside that has a negative 1 charge. So we've got a CN that's negative 1 here, we've got a BR that's negative 1. The charge on the CN isn't shown because it's attached to the cobalt, but if we switch these around, the CN becomes negative and BR is now attached to the cobalt. This is an isomer. It's a compound that has the same molecular formula but a different structure. Another kind of isomerism, it's a little bit more subtle, is called positional or geometric isomerism. And in an arrangement like this is called a square planar arrangement, where these two are actually in the plane of the screen, and this one's pointing back and this one's pointing forward, and they're all in the shape of a square. There's 90 degrees between these two CLs and 180 between these. That's actually enough to make them different. And these are 2 different compounds. This is cisplatin and this is transplatin. The other, another kind of isomerism is called optical isomerism. And in this instance, what we're doing is we're taking the mirror image of a compound and we're seeing if it's different. Now, this only happens if we have 4 different groups attached to the metal in the center. And in this case, we do. We've got a Br, we've got a Cl, we've got an I, we've got an F. Now, what this indicates here, this dashed line indicates that the Br is sticking back into the screen, and this indicates the Cl is pointing to the front. Now we take the mirror image, and now I want to convince you that the mirror image is actually a little bit different to what we started with. It actually turns it into a different compound. So here's an example, very similar. Let's pretend this is the chromium, then we've got the 4 other atoms attached to it. And this would be its mirror image. Now here's what I want you to see. If the mirror is down the middle here, there you go, there's the mirror image, there's your greens, there's your purples, and the reds are both pointing to the back, and the whites are both pointing to the front. Now what we can do is, let me turn this around 180 degrees. Now what I want you to see is that if I tried to line this up together, I could get the greens and the purples to line up, but now the reds and the whites will not line up. That's what makes these a little bit different. Now, this is a very subtle form of isomerism. The only way you can tell these two things apart is to put them into a special device called a polarimeter and to see which way they rotate plane polarized light. That's it. That's the only way you can really tell the difference between these two. And like I said, the only time this happens is when you've got 4 different things attached to a central atom. That won't happen at any other time in this sort of arrangement. Let me show you another example and just highlight why this doesn't happen in other cases. Let's say we've got a chromium now, and let's put a chromium with 2 Brs on it, and I'll show you what happens when we have 2 of the same thing attached to a central atom. Now again, this is showing the Br pointing back, and this wedge here is showing the Br pointing forward. And we'll make this one an F, and we'll make this one a Cl. Now if I take the mirror image here, not worrying about the counter ions, but just taking the mirror image, you'll see what happens. We can have the Cr there, and then we've got the F pointing back here and the Cl pointing here. Now if I do the same thing and turn this around 180 degrees just like I did previously, here's what happens. The F and the Cl will end up here, one pointing up, one pointing down, but still in the plane. And now the Brs will be over here. And as you can see, if you try and line these 2 up, you can line them up. The 2 Brs will match, the F and the Cl will match. So these are not stereoisomers. So there's no stereoisomerism coming on here. The only time we get stereoisomerism is when we've got 4 different groups attached to the central atom. Okay, there's another way that we can get stereoisomerism, and that is when we're using bidentate ligands. Now let me explain what this En business is. Alright, so let's say we've got this, oops, it's a nickel. Use the same one. And the En is called ethylene diamine, and it's called a bidentate ligand because it coordinates twice in the same molecule to the metal atom. Alright, so this whole thing here is ethylene diamine, and we just shorten it out to En, and we will often represent it like this, just for the sake of simplicity. So that's the same thing. Alright, so it's a little bit less complicated to draw it that way. Now I'm going to show you what isomers look like when we've got 3 ENs attached to a nickel. It's still in an octahedral type arrangement, and there they are. And what I've done is I've drawn them as mirror images. Now what I want you to see is we've got one here between, and this is going to be in the plane of the screen, and then we've got another one here pointing backwards, and that bond is in the plane of the screen, that one's pointing back, and then we've got another ethylene diamine at the front. See? Alright, this one's a mirror image. And you've still got this one at the front, you've got this one at the back, sorry, this one's at the back, and you've got this one in the plane of the screen, and that matches this one over here. So these two are actually mirror images of each other. Now what I'm going to do is I'm going to shift this around 180 degrees, and I want you to be convinced that these two will not line up when you try and line them up. Now you can get these two to line up, these are in the plane of the screen, and you can get those to line up, but look at the ENs here. This one's at the front, and now this one's at the back. You're not going to get those to line up. And this one's at the back. See this one here? That's at the back. And this one's at the front. So you're not going to get those to line up either. So those are also stereoisomers as well. And that's a nickel with 3 ethylene diamines attached to it.